Hey guys, very good morning. Thank you for joining with us today. I'm TN Pradeep Kumar Naidu, and this is going to be my new channel with the company Nikit Engineers. And today, the best topic that we're going to discuss is how do we solve or how do we weld a grommet and an igniter. Basically, these two parts are very essential in any aerospace industries. So let me brief you on that. But before that, you know a lot about Nikit Engineers, but I'll just give you a briefing. Nikit Engineers is an automation company. They're into welding, they're into civil automation, and we're also into WAS. That's welding as a service. Thank you. Yes, the problem that we are solving today is in regards to igniter and grommet welding, which is a very essential part in any of the aerospace industry, because welding these parts, as the size of these components is less than about 3 inches, that's about 75 to 100 less than that, and to weld these it's very critical because the weld joints pertain to a lot of cracks. So let's see how we're going to solve it, and let's focus more on the design portion of it and the costing, and we will get back to other details. So guys, let me take you through the components and the concept that we built for welding these components, and the configuration of the same, the costing, as well as the entire design process, the welding videos, and the kind of finishes that we've got. And there's a lot of things that we have added for you guys to download. So we are talking about these two components, guys. That is grommet. This is our first component. If you see the component, it has got a base plate of about 2 mm thick, between 1.6 to 2 mm thick, and it's got a small backing plate, on top of which there's a small cup-like curvature. This cup is about 8 mm in diameter. Now if we go back to igniter, this is again a much bigger component than the grommet, where the diameter is about 25 mm, and there is a curvature, which is our biggest challenge in our current process, as we need interpolation to happen all along the axis of the weld. Now this was our initial concept. So the initial concept was completely different from the actual machine, because we just gave an approximate ballpark design. So this was the actual design post the initial concept, where we shifted the entire design, assembly, and maintained OSHA standard guards all around the weld zone. Now let's come back to the components. Now depending on this component, for example, this is a 30 by 40 mm complete component area. For the grommet, it's a simple circular weld. Depending on these things, we decide on the axis that we use, basically x-axis, z-axis, rotary axis, and whether we need an interpolative system or a normal PLC. So based on the component, we make sure to ascertain what kind of control systems we need. So here in our current system, what we have done is, just a minute. So in the current system, what we have done is we have utilized not only a 3-axis system, we have also designed a particular fixture to make sure the component doesn't lift off. Basically, since it's a very small component, we need a fixture where the grommet, the top end, the cup sits exactly onto the fixture and doesn't move during weld, because the weld temperature here shoots up to 3000 degrees centigrade, because that's the arcing temperature for TIG. Even for grommet, if you see here, the kind of curvature that you see here is where our interpolative system comes into place, making sure there's a dip of about 1.14 to about 3.14 mm. That you can definitely adjust. So you can adjust the kind of dip that you want, and in the system we've done exactly that, so that the customer has got all the benefit of the system, of the control system, where he can program what dip he wants at which particular degree. Now let's move back to the concept. Here you can see Based on these component dimensions, we have assigned x-axis, z-axis, the kind of tip touch we need, and the clamping arrangement, the fixture base plate, the rotary unit, and we have not shown the, it's quite not visible about the wire feeding system. We have also introduced the wire feeding system here. Now if you can see the display on to your left, basically that was designed based on the company, the operator's feasibility for loading and unloading. Now, post designing the final, we call it the final DAP, the design approval process. When DAP process happens, we call in the customer to review it, to have a clear sense of what we are trying to build. Then we give them a particular costing, or we give this particular costing in the beginning and then add only the fixture costing later on. Right now we're showing you the exact amount that has gone through building this particular machine. This is the current rates that we have put forth. Basically, let's call this project number GL001, Grommet and Ignited Welding Automation. The process, as mentioned, it's TIG welding. The costing for it is control systems with display, basically a 3-inch display, about $1,230. Linear axis assembly, that is X and Z. We have also added the rotary system in the torch and adapter assembly rather than in the linear axis assembly. So the cost is about $710 for the linear torch and adapter assembly. The rotary is $495. Fixture assembly is about $1,060. This comes with the rotary fixture for igniter and grommet, all through EC copper, made from EC copper. Then frame and sheet metal about $640, safety system $310, and all inclusive project cost, that is the BOM cost of $4,445. But what we need to note here is all the motors are stepper and power consumption is hardly about 200 watt per hour only. Now, the non-inclusive costing. There are two phases of costing that we generally show to all our web viewers: costing and non-inclusive costing. Costing, it is only the BOM, and in non-inclusive costing, we refer most of the costing that is incurred by the company's different locations. For example, labor, all through design, procurement, inspection, assembly, electrical testing and training. Company overheads, again dependent on the kind of company that you have and the overheads that you feel. Consumables, welding power source, welding wire, gas and tungsten. Pretty much not of a difference here on the consumables. It's only depending on the location. Again, then the power consumption, then the installation cost, and packing and forwarding. These are completely independent. And depends only on the company which has to fix on this, because basically they put a margin, they add a 5% tax on services offered here. So these are the non-inclusive costing that we generally give for all our projects. Now let's go back to our project overview, where before going, just a reminder, a tagline of what are the companies that we are associated with. Basically 4 verticals: Nikit Engineers, Robotics, Welder, Civil Automation. All the 4 into different verticals, right from industrial, welding automation, Cartesian robo, welding as a service, and construction process automation. Fine guys, let us just a minute, let me see. This is coming back to our welding assembly. Basically, post determining the DAP and giving approvals for the process, the kind of costings, we go ahead after preparing the drafts to start over for our fixtures and other assemblies. Basically this fixture is designed for Grommet and igniter assemblies. They are based on the component we design the fixture, and as you can see, the fixture is made up of EC copper. All the fixtures that we do for such components are from EC copper. Basically it handles heat pretty much well, and it's the best conductor. There are again different variations in copper as well, as you may all know, commercial grade and other grades. So we focused only on EC grade here. So pretty much scrolling across all of the images, I would like to show you, yeah, this is an assembly just before the final testing, I think. Yeah, this is before final testing where we've just introduced the side guards, the front display panel that's on to your left, the front portion of the weld zone where the axes are situated. There's a side portion, there's a front portion, there's a front view where you've got 2-inch doors at the bottom. Basically, the first layer consists of your electrical wiring and electrical, what do you call, the complete electrical panel sits there, basically on the top, just below the fixture assembly. We make sure that all the electricals are sorted out here. You have the wire feeding motor as well. It's a DC motor, 24 volts. Now having this side view, yeah, this is our display. It's a 3-inch touch with type display from Delta. Then we have a sequence switch, a mushroom button for emergency stop and start, then speed regulator for the wire feeding control. Then we've got the main switch on and off, completely an automatic controller. Now moving on to the pages in the display. We have the calibration page of each motor, right from stepper motor 1, 2 and 3. Then we have other settings like the weld cutoff degree, speed of x-axis, speed of z-axis, speed rotary, interpolation speed, pre-tag delay. Pre-tag delay is nothing but the delay given before pre-tacking our components. You can set all these parameters at your own settings based on your component, and these are a standard in most of our system. And now moving on to the next page, basically this is where you can scroll. You can see the kind of date that we've done this project on. It's about, yeah, it's in 2030 that we finished this project. Yeah, this is another page that I would like to describe. It's completely about positioning, and this is a sequence page. Yeah, program 3 is nothing but sequence 3, basically, or recipe, that what, or we call it as a recipe. You can set all the parameters. Right now we have divided into 4 sections. Each section is about 90 degrees, and for that 90 degrees, what is the rotary positioning and what is the z-axis positioning. These are 2 interpolations that we have given. In case you would like to switch over from rotary to x-axis also, it's possible. So this is a homing page, the manual page, it's a main menu. Yeah, you're looking at the main menu. Most of our main menu consists of manual button, auto button, settings and calibration buttons. So that's it on the display, guys. So let's move on from the display to the actual welding. Let us just scroll around for our actual welding video. So here we go. I think we should have one here. For getting into the welding, since it's very difficult for during the welding to analyze the kind of interpolation that's, let us say, 1 mm or 1.5 mm. Let us go to a simple video, but before that, this is the one. This is the right video. Let me show you how interpolation happens. It's a pretty slow video here. Let me click it again. Just a minute. Just check. Yeah, here you have it. Basically, moving from, let us say we have started from 0 degrees. The component rotates from 0 to, right now it's moving close to 90 degrees. So moving from 0 to 90 degrees, what you observe here is there is a dip of about 1.14 mm right now in this particular component. That dip is automatically done through interpolation. Now from 90 degrees, the component rotary rotates to 180 degrees, where the torch tip again moves up by 1.14 mm. And in the entire sequence, the distance between the tungsten tip to the place of weld is about 1.622 mm. That's also the diameter of the tungsten that we've used. It's about 1.6. All during our testing, we varied from 0.8 mm tungsten to 2 mm tungsten. Now, if you see the positioning, it's moving back to 0 degrees. where it is setting back to what position it reached. So every quarter or every quadrant, uh, you can set the kind of dip the torch has to take based on the curvature of the component. Here we mentioned the dip because the component is only one, and if you have about a plethora of components, about 10-20, then we can give you an inbuilt sequence where you can just set the major dia, that is the external component, and the minor dia, that's the internal component, and the system can automatically detect the curvature. Now this is the testing video. So basically not much of a welding that you can see here. You can also see a clamper, a simple spring-based clamper to clamp the component prior pre-tacking. Let us go back to Grommet again. Yeah, this is the component that we had welded. This is another component, basically not the one which I've shown you in the video. This is the second component, the Grommet. See the kind of weld bead here. It's about 3 mm to 2.5 to 3 mm in weld bead width. That's the front lip. That's overlap. Now let us go back to the welding of the same. Just fast forward you to the right place. Yeah, this is it. Yeah, now you can clearly see how the fixture works. For Grommet, the clamping system, the spring-based clamping system, adds a minimal amount of pressure so that the grommet sits really well into the fixture during the weld, because the arcing, when arcing is done, the component tends to lift off from the fixture itself. So pretty much a 360 degree plus about 10 to 15 degree overlap of weld that we are giving here. What you might not see clearly here is the wire feeding process also, because that is also required. To have a 3 to 5 mm bead for such a small component, or 2 to 3 mm bead also, we have given a 0.5 mm feed rate of wire which just drips. So here you can clearly see how the weld bead looks. It's a very clean weld with the proper curvature, feed rate at about 0.5 mm per second to about 1 mm per second. Basically the wire we've used here is 0.8. The front lip intact, that's what is the criteria during all our welds, because the front end tip has got about 3 mm space where it ruptures due to heat. So let me show you let me show you a clear view of the components that we had done. That is, before final welds, what we do, we take a batch production or the T1 production. We've just got about 4 or 5 or maximum 6 components here, but we have done more than 100 components because this was the most difficult project that we've done during that phase. So we had to be sure the kind of process that we put forth in our systems. So let me show you the final finish of these components. Yeah, here it is, guys. This looks very clear. Yeah, on the left is the actual component, on the right is the welded component. You can see the kind of curvature also. Without interpolation, that would be a very flat weld bead. Yeah, now for this component as well, you can see the front lip. The front lip is really low, so the finish has to be really good, and the overlap or the wire feed also has to be very, very minimal. So apart from these guys, we also have some interesting stuff for you to download, like our costing sheet, and further you can also download our 3D or other project details. Thank you so much for watching, guys.